Hadrons are made of quarks. There are a total of 6 quarks, and each quark has its antiquark. So the 6 quarks are up, down, top, also called truth, bottom, also called beauty, strange, which is also sometimes called sideways, and charm. Mesons are made of 1 quark and 1 antiquark. And baryons are made of 3 quarks. Antibaryons are made of 3 antiquarks. So the quarks can actually have a fraction of a fundamental unit of charge. The up quark has a charge of 2/3 the fundamental unit of charge. The down quark has a charge of minus 1/3 the fundamental unit of charge. So since a proton is made of 2 up quarks and a down quark, it has a total charge of 2/3 plus 2/3 minus 1/3 and a sum of 1 fundamental unit of charge. The neutron, on the other hand, is made of 2 down quarks and an up quark. So it has minus 1/3 plus minus 1/3 the fundamental unit of charge plus 2/3 the fundamental unit of charge, which sums to a total of 0 fundamental units of charge. So the neutron is neutral. So because the quarks have a fraction of a fundamental unit of charge, is it possible then to ever see a fraction of a fundamental unit of charge? The answer is still no, because quarks do not live alone. They always live with an antiquark or with a couple of other quarks, so that the sum is always a total of a fundamental unit of charge. Even if you try to rip a quark out of its particle by smashing particles together, quarks will grab other quarks out of the vacuum, out of just the energy of the reaction. Other quarks will be instantly created so that the quarks are not alone. Quarks are never alone, and their charges always will add up to some fundamental unit of charge. So let's take a look at this example problem. We have a reaction where we have a pi0 meson and a neutron goes to form a K plus and a sigma minus. So if we know that the quark composition of the neutron is down, down, up, the pi0 is up, anti-up, and the composition of the K plus is up, anti-strange, what is the quark composition of the sigma minus? So let's rewrite this reaction. We have our pi0 plus our neutron, and that goes to form the K plus and the sigma minus. So the quark composition for each of these particles is given. So for the pi0, we know that we have an up, anti-up. The neutron is a down, down, up, and that goes to make a K plus, which is up, anti-strange, and then we have this mystery particle. So we can figure out the composition of the mystery particle by conserving quark type. So if we look at the type of quark, if we look at each type that's represented here individually, let's start with the up quark. So for the up quark, we can represent up quarks as a +1 and an anti-up quark as a -1 for upness, let's call this. So we have an up and an anti-up, that sums to 0. We have an up quark here in the neutron, so we have 1 up quark there. So that goes to 1 up quark here. So this is a single up. And then, well, we already have a balance in up quarks, so this mystery particle would have no up quarks. So we notice also that we have down quarks involved, so let's conserve down quarks. So here there's no down quarks. Here we have 2 down quarks. That goes to no down quarks. So we know this mystery particle needs to have 2 down quarks. So we know that there's going to be 2 downs in that mystery particle. So then the third type of quark we have here is a strange quark. And strange particles have strange quarks. So we have no strange quarks in the pion. We have no strange quarks in the neutron. And we have a strange quark here, but this is an anti-strange quark, so we'll represent that as a -1. So we're going to need 1 strange quark here to balance the strange quarks on this equation. So we need 1 strange quark. So we have, for our mystery particle, we have 2 downs and a strange quark. So the quark composition for our sigma minus, that would be equal to down, down, strange, or strange, down, down if you prefer. So next, let's look at this question. In the following reaction, what is the missing mystery particle?